we are going to talk about trusted execution. Okay, so let's first start with the basic idea. So the basic idea is that we have this operating system, whether it is our computer or desktop computer, laptop, or a mobile phone. So we are using some sort of operating system there. That I'm referring as the regular OS, regular operating system. Now we are installing applications on this operating system, and therefore although we may have a variety of intrusion detection techniques, a variety of preventive techniques, but it is always possible to miss detection of malware or uh, inability to prevent a malware from infecting your device. So this can always happen, and you see that in the news and in the media. You will see that there are always some systems or devices which are getting attacked by this variety of malwares. Okay, so then what is so there people have been looking into a variety of things and um, how to manage this scenario. And one very neat idea is to have some sort of isolation from the regular OS, which means that so you have this two-layered architecture. Okay, so let me just draw this. We have these two layers where the layer 1 has the regular OS, where this regular OS may have these different applications. It may have a memory of its own, it may have a processor. So all the things that a regular OS has, it has all those things. But then we also have the basic idea is that we also have something in the hardware. Okay, so the basic idea started with the hardware that so the OS will be running. So OS is a software, it will be running on a hardware, but what the difference here is that the applications are installed in the software. Okay, but we have something, some trusted execution capability. So let's just say execution capability which could be trusted in the hardware, which can do a variety of things. So first thing is that there has to be isolation, which means that this trusted execution capability that we are providing to this separate hardware, it has its own memory. So it has its own memory, it has its own processor, um, so that it could run compute things. And then we also have some secure way or very controlled way of communication between the regular OS and the that trusted execution environment that we are creating here in the hardware. So what we are saying is that you have this two-layer architecture where one layer will have the conventional regular OS, where you will install applications, you will work on that application. So everything that you will be doing as a user will happen in the regular OS. But then there is this second layer. So this is the layer 1, and then this is the layer 2, or you can say actually the layer 0. So this is the layer where things are in the hardware. There is very limited communication between the regular OS and the hardware. There is very limited way that you could communicate between these two. And since this is in the hardware, it is not possible for a malware to make changes. So the malwares make changes uh, in the software. So if an adversary, if an attacker does not have physical access to your device, then it will not be able to modify your hardware. So we are saying in this layer 0 or layer 2, we have a hardware-based environment which has its own memory, which has its own memory, which has its own uh, processor, and it could do computations on its own. So isolation from the regular OS is a basic idea that people started thinking about. And then the security guarantees come from the fact that this layer 0 will be implemented in hardware, which cannot be remotely compromised. So an attacker sitting remotely can send malware to your device, but it cannot physically tamper with your device, and therefore the security guarantees come from that fact. And then, notice that if we implement everything in the hardware, it might be a little difficult to do any kind of reconfiguration if it is needed. And therefore, this limited communication between the regular OS and the hardware on which things are being implemented, that is what is allowed in order to do some minor reconfiguration to the trusted execution environment, or retrieving some information from the trusted execution hardware-based trusted execution environment from this layer 0. So these are some basic ideas behind trusted execution, that rather than have, so we have been looking into different architectures. So we looked into how to prevent attacks, we looked into how to detect attacks, but now what we are saying is that we have these cryptographic techniques, but they may not be sufficient. We have these detection techniques, but that might also not be able to detect some attacks. So therefore, let's say that our regular operating system is always vulnerable to an attack. So then what can we do? So then what we are saying, that let's have another layer which is implemented in hardware, and then let's see if we could do some things with that or not. And what are the things that could be achieved by this isolation, by this method of providing security? We will talk about it. But the basic idea is that let's have some sort of hardware-based security guarantees. Okay, so is the basic idea clear that or the basic idea is to have this two-layered architecture and the basic aspects of this two-layer architecture? In fact, let me go to the next slide. Yeah, I can take some questions. Okay, so let me take some questions after explaining this nice architecture through this figure. Okay, so the two layers that I have talked about, they are expressed in different ways. Okay, so different industry stakeholders, they talk about this two-layer architecture in different ways. So ARM talks about it in this way. So the architecture that I am showing you here is basically from provided by ARM. Okay, so the ARM, according to ARM, so these two layers could be called a secure world and a non-secure world. Okay, so again, these are the two layers. Okay, so in the non-secure world, so non-secure world can also be considered rich execution environment. That it just means that you can do everything as a user in this environment. You can install untrusted app, so that would be completely fine. And there could be some embedded OS as well. So this is not just a simple computing system, but ARM also focuses on these embedded devices. So therefore, you can have some embedded OS there as well. And of course, this embedded OS will need some memory, some processor. So it will have access to all that hardware as well. Okay, so that is the non-secure world. And then we can have a secure world as well. The world that I'm saying that could do this trusted execution. So therefore, it is named Trusted Execution Environment, and or TE. And there you will have only trusted applications. So these are not the applications that a user could install. So there might be some applications, there might be some functions running, but they will be pre-configured, they will be burnt into that hardware, and you may not be able to readily reconfigure them. And then you will have this trusted OS running these trusted applications, and this trusted OS will have access to protected hardware resources. So it may have access to memory, it may have access to a separate processor. It is also possible that some of the processor that is running, there might be just one processor, it might have multiple cores, and one of the cores is actually working for the secure world, other cores are working for the non-secure world, but then there is still some kind of isolation between different cores of the processor. So this is the basic architecture of this idea of trusted execution, which is very, very popular. So I will tell you that these ideas were there since 2000s, and any computer which is shipped after 2008, or any tablet which has been shipped after 2008, all of them has some sort of hardware which has this ability to do trusted execution. So these hardwares were initially called TPMs, trusted platform modules. And you can always use these trusted platform modules to ensure higher security level for your computing platforms. It's another matter that it is not very user friendly, and therefore it has this so since this has been there since 2008, people had expected that this method of securing systems would actually take off. Some systems do utilize them, but although this ability is present in your computing systems, but not many people utilize it. But that is another matter. But still, people are hoping that this idea with increased reconfigurability. So recently, people have been increasing the amount of reconfigurability that you can have in the trusted execution environment, and with sufficient reconfigurability, with sufficient user friendliness, probably this idea will become more and more popular. Okay, so any question about the basic architecture of this trusted execution environments?
Sir, can an application be tested in the secure world?
No, so typically you cannot, a user cannot install anything. So of course we have these simulation environments for TE. Okay, so simulated TEs, so where you just simulate a TE, and then you have again a simulated OS. So in that, you can think of it as a testing framework. So in that simulation environment, so simulation is in the software. So in that simulation environment, you can have any application in the TE and test how it interacts with the simulated OS. You can test all those things in that simulated environment. But once these trusted executions environment-based devices are shipped and bought by users, they cannot test any new application in the trusted execution environment.
Like, sir, why don't we use a trusted execution environment in every computer? I mean, is it costly, or is it time consuming?
Yes, so the thing is that again, it is about reconfigurability. So would you like to buy a phone where you cannot install any new application? So that is the question. But you would always like to, as a user would always like to have a system which is easily reconfigurable. It becomes really difficult to work with a system given by your enterprise when you cannot install anything. So therefore, you have probably, many of you, if you go to the industry, you will have two computers. One will be your personal computer, and one you might be using for your office work. And the laptop that will be given by your office for the office work, you may not be able to install many applications um, in that laptop. So it is more about reconfigurability, user friendliness, that prevents this idea of trusted execution, or which has actually stopped this idea of trusted execution becoming very, very popular. So yeah, I guess that is the fundamental problem. But then there are other issues, as you have said. Cost is definitely something. So what happens is that you have this rich execution environment and you have this trusted execution environment, and you have let's say some hardware. Let's say you have processor which has this 4 cores, and now you give 3 cores to the rich execution environment and 1 core to the trusted execution environment. So now you, your rich execution environment is not able to utilize all 4 cores that it could have utilized when this trusted execution environment was not there, or would not happen there, or is not enabled. So definitely having trusted execution environment has some cost, um, and yeah, it depends on the application, whether you would like to have such cost incorporated in your system or not.
The one last query, sir. Sir, like communication can happen between the non-secure world and secure world, sir?
Yes, so communication can happen. So it can happen, but it is very, very limited. Okay, so it
And sir,
is
like
very, very limited.
what
Uh,
type of communication is this?
Yes, so it will be something like from the non-secure world, you can send a message, um, which you can send a message. I will talk about some applications, and there I will also talk about it, but let me also say very briefly about it here. So from the non-secure world, you could probably call a function. Okay, so probably that would be the better way to say it. So these applications that are running, you can think of similar applications, similar functions that could be executed in this environment. And from the non-secure world, you can call those functions, and then you could get response from those functions. So you can use those functions as a black box. You give inputs to those functions from the non-secure world, and then you could take out um, the results or the output from those functions.
So thank you, sir.
Okay, and this trusted execution environment also has a way to read the whole memory. So whatever memory that is available for that system, typically this hardware can actually do a read only. So probably it will not have any write. So typically you will not give write access, but you will always give it a read access to this hardware environment, where you could read from whatever information is stored in the hardware. So that is also available. That link is also utilized for that purpose. Okay. Okay. Any other question about this idea of having this two environments on the same system, and having these two operating systems on the same system?
Sir, this trusted OS is something inside Windows.
Sorry.
This trusted OS is separate from Windows OS that we are using.
Yes. So there will be. So if so, your at least let's just talk about trusted platform module. Okay. So um, any device that you might be using, if let's say it is a Dell laptop with Windows operating system, it will have a trusted platform module. Okay, so that can actually do trusted execution. Okay, so what you could do is you could have uh, some keys that could be stored in the trusted platform module, and those keys could be utilized to do a variety of things. So if you, so in these cases, what you need to do is first, typically they are not enabled. So these trusted platform modules are not enabled. So first you will have to enable that trusted platform module. So once it is enabled, then these keys that are stored in the trusted platform module, you could utilize those keys to probably do some encryption of some information that is present on your Windows environment. Now, if you do that, even so, in that scenario, even if your complete Windows operating system gets compromised by a malware, whatever you have secured using the trusted platform module, that remains secure. So it is another matter whether you could recover your operating system or not. So we will talk about that as well. But yeah, so recovery is another matter, but at least the trusted platform modules in all computing systems that are shipped after 2008, they have this ability to securely do some cryptographic operations on some information. Okay, so that can be done. But recovery, so there has to be some additional things that needs to be done in addition to having secure hardware. So you need this whole thing. You need this whole environment for recovery. You need to have a trusted OS running. You need to have some applications running if you want to recover. So what I'm saying is that in the non-secure world, if the whole non-secure world gets compromised, then if you have a secure world which has all required trusted applications running, then you can recover the whole non-secure world operating system as well. But at a minimum, if you are not running these trusted applications, at a minimum you are just using a trusted platform module, then at a minimum what you could do is you could probably encrypt some information in your non-secure world and store that information in the non-secure world to easily access them. So even if now what will happen, even if your non-secure world gets completely compromised by a malware, even in that case, the information that you have encrypted using the keys that were stored in the trusted platform module, that remains still secure. Okay, so I hope this difference between securing information using this idea of trusted execution and recovery of your system. So both these things are possible. It's just that typically systems have this capability of having secure information, but recovery requires significantly more trusted applications running in the trusted execution environment. So recovery may not be possible in your Windows platform, but yeah, it is possible in many other systems. So we will talk about some of those in a few minutes. Okay. Okay, so now let's talk about the basic application of the first and the basic application of trusted execution. Okay, so you now understand that there is a way for us to do some computation in the hardware, and then so you now know that from the non-secure world, you could call some functions and some operation will run in the secure world, and the results will be sent back to the non-secure world. Okay, and then that the secure world also has access to all the hardware that is there. Okay, so which means it has access to all the memory that is there. Okay, So now what can be done? We are looking into what are some of the applications in which this basic idea could be utilized. And the first application has been to do attestation. And what is this attestation? So let's say that your non-secure world is running one operating system. So it is running one OS, which is so of course you could install new applications. So you can install new applications, but the basic OS is not changing very quickly. So you will get some updates, and then the basic framework of the OS might change, but those updates are very spaced in terms of time. So you do not get regular updates, do not get very quick updates. So if the basic code for the OS, okay, so if the basic code of, we are assuming that the basic code for OS remains static for quite some time. Okay, so if the code of that OS remains static for quite some time, then what we could do is we could very easily compute a hash of that code. Okay, so we could compute the cryptographic hash. We can use any algorithm. SHA-256 is perfectly fine. So we could compute the hash, and if that hash is stored in the secure world, okay, so if I know that I'm not going to change this operating system for a very long time, we could compute the hash of the code, and then we could securely store the hash in the secure world. Okay, so the hash is now stored in the secure world. And then what will happen? So this is what we will start with, that we have a OS, we have the code corresponding to the OS, we have computed a hash or digest of that OS, and we have stored that digest in the secure world. So that is the starting point. Now in the runtime, in the operation phase, this OS will be installing many applications, uninstalling many other applications, working fine. But at any time when the secure world wants to see whether this OS has been compromised by an attacker or not, what it can do, it can trigger this process which is called attestation. And what will happen in that process? What will happen is that this secure world will read the memory where the OS code is written, and it will access the whole OS code. It will compute the hash, and then once it has computed the hash, so hash during the operation of the device, it will compare that. You can call it runtime hash. Okay, so runtime hash will be compared with the stored hash. So it already had the store. It already had this stored value of the digest in the hardware, and at runtime, it has done. It has computed the hash, and it will try to compare these two. If they match, it means that the OS has not been compromised. If they do not match, then the OS has been compromised. So that is the way of static way of attestation, where what we are doing is that we are assuming that the OS code remains static, and the corresponding hash has been stored in the hardware in the secure one. And during the runtime, when the user is actually working on that OS, at any time, if the secure world wants to trigger this process of attestation, it can trigger that. And once the secure world triggers it, all the memory will be read, the hash will be computed, and it will be compared with the stored hash. And that will be the way to figure out if the OS code has been changed or not. Okay, so is this basic way of testing or making sure that the operating system, if the operating system is compromised, then it will be detected. Is this clear? Okay. Is this not clear?
Sir,
It's clear.
sir, it means that there will be no updates once uh, I mean, once the system is shipped out.
Yes. So that is what we are talking about here, that there are no updates. But I will talk about the scenario where we will have updates. So dynamic attestation will also come. But yeah, at this point, we are not assuming. So this was the first application of trusted execution, and that is why I wanted to talk about it first. So this was envisioned that this is the way trusted execution will be utilized.
Well, in case of our mobile, which the OS is not upgraded like without human intervention, so in that case, this static attestation will work well.
Yeah, that is fine. So if the corresponding hash is stored in the secure world, uh, the hash of that of whatever operating system, if it is stored in the secure world, it can work. Okay, so the final goal is to make sure that whatever is stored in the secure world could be compared with the runtime hash. So in any scenario, if you could satisfy that condition, then things will work. So that is not a problem.
Sir, when you install a new application, there are no changes to OS code as such.
No, there are no changes to OS. Typically, the OS code remains unaltered. So this is just application that will utilize the OS, but it is not directly changing the OS. And if it is
Sir,
changing the OS,
what about
it can. Yes, please go ahead.
sir, what about the systems which has multiple OS? Like in example, sometimes we boot our computer with multiple OS. So whenever we switch to next OS, like the previous data of previous OS should be removed, right?
Yes, so the different OSs could be there on a system. So in this way of static attestation, I guess the solution could potentially be that you have multiple hash values stored in the secure world for these different OSs. So, okay, so let me tell you what can happen and what is typically also done in many existing systems is that when this booting starts, okay, so when you boot your system, at that time, even at that time, so of course it has significant overhead, it delays the booting, but what can happen is that while your system is getting booted, the secure world, so every time your system is getting booted, the secure world will compute the hash and it will compare the hash value with the stored hash value. So every time you boot your computer, even before the booting, so remember this is a separate operating system which is running. So this operating system that is running in the secure world can boot first. Okay, so let me just go to this figure. So this trusted OS is the one which could yes. So this trusted OS which is here, it could boot first, and once it has booted, then what will happen is that it will compute the whether this OS, in this case embedded OS, has been altered or not, and your original operating system, which is connected with the user, where user is actually installing and doing stuff. So that will boot only if the hashes match. Okay, so the stored hash and the hash of that current version of that OS, if they match, and only then the embedded OS in this case will boot. So that is also something that could be done. So now whether you have one OS or you can have multiple operating systems, all of them can work even in this setup where you are preventing even the booting of starting of that operating system if that operating system is compromised. So that is also something that could be done.
Sir, but this to work, we need to store hash of that OS first in the hardware.
Exactly. Yes.
But like we don't usually change the hardware, so it's how do we like store in first and the
Yes, that is a perfectly valid question, and that is why I said that uh, the initial version of these trusted executions environments, the initial applications, they had some reconfigurability issues, and but people have actually come up with more ideas to how to make it more reconfigurable, which means that what happens if the operating system gets updated. So how to handle those scenarios. Let's use the trusted execution environment, but also allow the OS update as well. So yes, so people have been thinking about it. So I have just started with a very basic application which was developed, which was proposed in the initial days of trusted execution, and then I will move to uh, more dynamic environment. Yeah, I will be talking about it in just a minute. Yes. Any other question? Yes.
This concept is applicable to virtual machines as well.
Yes. It is. It could be applicable to virtual machines as well.
Sir, assuming that since trusted execution environment is a pre-configured hardware where only read permission is there and no write permission, sir. Sir, and assuming in this case we have only static OS where there is no OS upgrade. So, sir, in this case, trusted OS can be used. In the non-secure world, only a trusted OS can be used, which is burnt onto the hardware with no write permission, only read
No, no,
permission,
no.
sir.
So trusted OS cannot be used directly by a user. So there is no user interface to actually install an application in the trusted OS. Okay, so you cannot. So the user cannot directly interact with the trusted OS.
Right, sir. Right.
Yes, yes, that is not possible. Okay. Okay, so now let's look into more dynamic environment where things are changing, where the OS is getting updated. So for that, there has been a mechanism which is also called remote attestation. Okay, so the dynamic term can refer to anything. So let me just give you one example of remote attestation, how it could be done. Okay, so let's say we have Microsoft here, and it has this Windows platform, and then we have our uh, this non-secure world and the secure world. So this Microsoft sends updates to this non-secure world OS, and it also has the system. This whole system has the secure OS as well. Okay, so what can happen is that the Microsoft will be sending these updates on the internet. Okay, so the interaction will happen through the non-secure world. So the non-secure world is the only thing which is connected to the internet. Secure OS is not connected to the internet directly. It always interacts through the non-secure world. Okay, so what can happen is that so it has a version of operating system. Okay, so this system may have the version of the operating system. It can tell Microsoft what version it is using. Microsoft may have the hash of that version of the OS. Okay, but what it will do is, for freshness, it will send a random number or nonce. Okay, so it will send a nonce to the non-secure world. Okay, so first thing is to figure out that what is the current version running on the non-secure one. Second step is that the Microsoft will send a random nonce. Now, and it will, okay, so first also I need to also highlight is that there is a way that the secure OS, so the public key of Microsoft is stored in the secure OS. Okay, the secure OS has the public key of Microsoft. Okay, so when the random nonce is sent, it will of course be signed using the private key of Microsoft. Okay, so then this nonce will reach this non-secure world and then forwarded. Now, once the secure world sees this random nonce and this request to do attestation, and it sees the digital signature on it from the Microsoft, it will be able to verify the signature using the public key of Microsoft. Okay, so once the nonce is verified, once the request to do the attestation is verified, then this secure world will go ahead and read the memory, the code, OS code, and in that OS code, it will also concatenate this random nonce. Okay, so it will concatenate that random nonce. Small 128-bit nonce is sufficient, and a hash value will be generated. Okay, so it will generate a hash value. Okay, so now note that if the nonce is different, this generated hash value will be different each time. And this now generated hash, it will be signed by its private key. Okay, so again a digital signature, and its digital signature will be, its public key will be known to the Microsoft. Okay, so this is also important that the public key will be known to Microsoft. So it will sign the generated hash, will send it to the non-secure world, and the non-secure world will forward it to Microsoft. And now Microsoft will take that version of the OS. It will also concatenate the hash value, and it will compute a new hash, and it will try to compare the generated hash with that hash that it has received from that system. And if they match, then things are fine. So that the same version is running on that system. And you see that if the update happens, then there is no problem. So Microsoft knows that this is the version that has been updated. This is the hash that I could expect if I do not have a nonce, but it always adds that nonce in order to make sure that the non-secure world does not just replay previously calculated hash value. And in order to prevent that replay attack, it adds that nonce value. Okay, so this is what happens. Is it clear to everyone what happened in this dynamic environment where updates are also possible and reconfigurability is possible? But now in this case, we need a trusted third party. So Microsoft in this case is the trusted third party which has actually did the comparison. And of course, after this comparison, it could send back the response to the secure OS that yes, it is fine. You are running the operating system running in the non-secure world is has a valid hash and it has not been compromised. So that information could be relayed from the Microsoft to the secure world of the system. So that can always happen. So you see that this involvement of a trusted third party, Microsoft in this case, will now facilitate this dynamic environment. Is it clear what happened here?
So the hash verification is done by the Microsoft.
What is typically done by the Microsoft?
Hash verification?
Yes. So in this case, hash verification was done by Microsoft. That is our trusted third party in this case.
And when is the new hash being generated after the update?
So the new hash is generated at secure OS. So secure OS is the one which will generate the new hash. Okay, so the some computation has to be done by the secure OS. So what are the two important computation that has to be done by the secure OS? First is reading the memory corresponding to the OS not running in the secure one. So reading the memory has to be done by secure OS. Okay, so someone sitting remotely cannot read the memory. Okay, so reading the memory has to be done by the secure OS, and then computing the hash. Okay, so you do not want to send the, so another solution could happen that you read the memory, secure OS reads that memory, then probably encrypts it, sends it to somebody, and then to Microsoft, and then the Microsoft computes the hash. But that is probably not a good way. So what the secure OS does is it reads the memory corresponding to OS code, it computes the hash of the current OS that is running on the system, and then it sends that hash to Microsoft. And since Microsoft knows that this should be the hash of this version of the operating system, so it will be able to figure out whether the received hash from the secure OS is the correct relate to a correct version of the OS or not.
So the prerequisite for this process is connectivity of internet. Suppose some system is not at all connected, then this cannot happen, right?
Yes, this cannot happen. So let me bring in an interesting perspective. So I will talk about it right after this. So digital rights management. So remember, if you are using any platform which has this Windows operating system, then you need to have a license. Okay, so even many of our ITD students, they have this ability to freely update the license from through our ITD network, but they do not do it, and therefore you will see a message that your license has expired, even for the Windows. Your license has expired. So so of course so these kind of things are possible. So people, when they want to make sure that this license, the existing license could be reutilized, so they do a lot of malicious things. For instance, changing the clock of the computer that they are working on, or changing some registry file which will allow them to use that, or making sure that your system is not connected to the internet. So if your connection system is not connected to the internet, and you refresh the time and make sure that you do not get that error, then the next time you won't get an error. So Microsoft definitely utilizes your internet connection to read the version of the operating system and whether you have the license or not. So that actually happens over the internet. So if you're not connected to the internet, then that will not happen. Okay, so now that you have learned about how this attestation could happen, I have already said it, but can someone tell me how this digital rights management could be enforced? So digital rights management is that if Microsoft says that your computer should have Windows 10, okay, because you have paid for Windows 10 and the Windows 10 Home Edition. Okay, so if you have paid for this, you have obtained a license for this, then your system should be running this Windows 10 Home Edition. It should not be running any other Windows. It should not be running Windows 11. It should not be running Windows 10 Professional version. It should not be running those things. So how could this idea of trusted execution be utilized to enforce digital rights management? How can Microsoft enforce that whatever version, whatever license you have purchased, you are running the same on your system? How can this be done? Can someone tell me? Using this idea of
So
trusted.
like say Sir, since like trusted environment can be updated through Microsoft, so if we like they can like store hash of the original Windows 10 in a secure environment, then if user tries to run Windows 11, then the hash won't match to the stored in the secure, and the error will be error.
Yeah, yeah. I guess your voice was breaking, but I think you have the correct idea. Anyone else would like to add to what Vijay said?
Let's say possibly Microsoft manages some database of which hardware ID has which version, and then stores the corresponding hash, and then periodically checks whether this system is having the same OS or not.
Yes, yes, that is correct. So that can be done by Microsoft. So similarly, so this is about operating system. Now you could actually now start thinking about this multi-tiered architecture as well. For this, I think, yeah, I can talk about this multi-tier architecture here as well. Okay, so we talked about this that you have this trusted OS running on this. So this is the same system. So this is the same system, and then we have this untrusted OS, which was also running there. Um, but through the trusted OS, we were able to make sure that that untrusted OS cannot be changed. Okay, so now this untrusted OS, you also have some trust in this untrusted OS, isn't it? That although it is running in the non-secure environment, because it cannot be changed and it is being enforced by this trusted OS that it cannot be changed, then this untrusted OS also has this trust now that you have in this untrusted OS. So now this can be thought of further, where now you are thinking about these non-trusted applications that you are installing on this untrusted OS. But this untrusted OS is also running an application, so which is coming as part of the OS. It is not a new application. It is something which is part of the OS, which actually has this. So you can say it integrity check module. Okay, so let me just call it integrity check module. So let's say this integrity check module comes as part of the OS. Okay, so when this trusted OS is computing the hash, it is also computing the hash of this trusted check module. Okay, so as part of the whole OS. So this integrity check module cannot be compromised by an attacker, and it might evade detection by the OS. That will not happen. So integrity check module is now trusted. Okay, so now that this integrity check module is now trusted, so what you could do, so now this untrusted OS, through this untrusted OS, you could actually compute the hash of any application that is running on your system. Okay, so you installed an application, it was non-trusted, but its code is again, let's assume that it is static, and when you installed it, you computed a hash of it, and you stored it in that integrity check module, and after a few days, you again compute a hash of that application, and you compare with the hash that you have stored in that integrity check module. And if the hashes match, it means that your application has not been altered with. If the application has been changed by a malware, then you will detect it. So this you will detect it through this untrusted OS. Okay. So again, this is the static environment. Now looking forward, again the dynamic environment for this application would be that whatever is the application developer, let's say it is Netflix. Okay, so Netflix wants to make sure that you are running the original, their version of application, and you have not played around with their application. So what it will do, it will ask your untrusted OS that, okay, you have this integrity check module, tell me the hash of the application, the Netflix application running on your system. So then this will respond back with the corresponding hash, and this Netflix will do this remote attestation that we just talked about. So this is the layered, so this is now the third layer. So we talked about this trusted OS and untrusted OS environment. And now we are talking about an application which is actually being secured by this integrity check module. So now we are moving the trust. So you have this trusted, so we had this trust in the hardware based trusted OS. Now that trust moved to the untrusted OS because we were matching the hash value of that untrusted OS, and that trust now moved to that application as well. So non-trusted application as well. So people have been talking about this zero trust architecture, where they are utilizing multiple components. So this is a very catchy term, zero trust. So what? So there are many things that are being utilized as part of this zero trust. Many components are there. One of the components is that, okay, so Netflix does not trust its users that they will not alter with its application. So therefore, this could be a way the Netflix could make sure that all users which are using its application, they are running the correct version of the application. So is this idea of digital rights management also clear? How the application version could also be verified by somebody, not just the operating system, but the application version could also be verified or managed by this different vendors, for instance, Netflix, because of this chain of trust. Okay. Okay, so similar ideas are being utilized for mobile payments, cloud services. So these uh, large enterprises which are actually giving out these cloud services, they're also worried about these kind of attacks, recovery of their systems, and therefore this idea of trusted execution is probably getting more accepted by large enterprises than these more public users. And of course, this idea of two-factor authentication has just been accepted by the public now. Hopefully, soon this idea of trusted execution will also be. Because let me conclude this lecture with a few highlighting few actual real-world implementations of it. So ARM is so remember there is a hardware component here as well. Okay, so trusted OS is there, but the trusted OS has to be implemented in this architecture which supports that trusted OS. Okay, so support of trusted OS has to be in the hardware, and ARM is the one which develops that hardware, which is called TrustZone. Intel, okay, its name is not there, but Intel has this environment which is called SGX, Secure Guard Extensions. So that is also there. So these are hardware facilities which could be utilized by the trusted OS. And now, which are those trusted OSs? So different companies have different OSs. So let me just talk about some famous ones. So Opti is by Leonardo, which is very popular for embedded devices. We in our lab we utilize Opti for a variety of testing which is directed towards IoT devices. So we utilize Opti quite often. Of course, these different Apple, Google, they have their own trusted OS that could be run there as well. Okay, so this is probably a very short list. So people are developing their own trusted OS as well. So of course, it is just developing a regular OS is difficult. Developing a stable trusted OS is more difficult. Okay, so I think I have already talked about it in more detail. Okay, so I guess any last questions before we end our discussion today?
Sir, there is also some sandboxing mechanisms available
It
in
is
soft.
just a term. Sandboxing is just a term. So, which means that you provide reconfigurability. So, it is just a term which is typically utilized in many different scenarios. Just by saying sandboxing, it does not mean anything, but it just says that you have this reconfigurable environment which could do anything. So that is basically what sandboxing is. Now, if we think of it as in trusted execution environment, what we are looking at is that this trusted OS that we have, it has more reconfigurability. So that sandboxing idea is taking this idea of trusted execution towards more reconfigurability, and that is the goal. So we want to make sure that this idea becomes very popular, and it would be possible only if it is more reconfigurable. So hopefully you will identify some challenges and think about, even in that dynamic environment, are there some issues where this idea of trusted remote attestation uh, may have some limitations. If you start using it in a regular environment, you will feel that there are still some um, issues, and yeah, so we definitely work on some of the issues. Some of our students are working on those issues as well, but yeah, I don't want to bring those issues here, but these are the basic uh, ideas on which trusted execution environments work, and of course there could be many different ways in which this idea could be utilized. So we know that from our experience that this Opti is very stable, but yeah, we have not tested any other trusted OS. Okay, good. So let's talk again in the evening. So remember, this is the lab session I have scheduled it to start at 5 p.m. today. So not at 4, but 5 p.m. Okay. Okay. Talk to you later then. Bye bye.
Thank you,
Thank
sir.
you, sir.